This UCSD TV program is presented by University of California Television. Like what you learn? Visit our website or follow us on Facebook and Twitter to keep up with the latest programs.
Good evening, I'm Dan Atkinson. I'm the Director of Public Programs for UC San Diego Extension, and it's my pleasure to welcome you for this evening's talk with Dr. J. Craig Ventor. This is the opening event in this year's Helen Edison Lecture Series here at UCSD. It's my pleasure now to introduce our interviewer for this evening, Roger Bingham. Roger is a member of the Computational Neurobiology Laboratory at the Salk Institute and the Institute for Neural Computation at UCSD. Roger follows in the footsteps of his great predecessor at the Salk, Jacob Bernowski, as a passionate and erudite advocate for science education, having been the creator and host of Emmy Award-winning PBS science programs. He is also the co-founder and director of the Science Network, an online trove of video programs on many topics in science, and that can be found at thesciencenetwork.org. So please join me now in welcoming Roger Bingham, who will introduce Dr. Ventor.
Thank you, and good evening, and welcome. Although Dan said it will be an interview, it won't. It will be a conversation. We don't know where it's going to go. But then, that's kind of been your life, hasn't it? Craig Ventor, let me just briefly say, founder, chairman, and CEO of the J. Craig Ventor Institute, also founder and CEO of Synthetic Genomics, and also a recipient of the United States National Medal of Science. We're here because he has a new book out called Life at the Speed of Light, From the Double Helix to the Dawn of Digital Life. And this is a particularly good place to do this because he actually graduated from me here. He got his PhD here, and you can't drive around this area without running into a Ventor building. They're at both ends of the mesa. There was a new one going up at the moment, which will open on November the 8th. And there was a 9th. There was a huge piece in the San Diego Union Tribune recently, which I hold up here, shows Craig inside the building. UC San Diego graduate and genomic trailblazer brings star power to La Jolla's lustrous bioscience cluster. But I sent him an email about this, because on here, what they've done in post is to put on the supporting pillars here, rockstar presence. And I did email him and say, are those words actually on the building, or are you going to put them on the building later? So,
well, you like them so much, we're going to add them now.
I think you should. Let me lead you into this book. This is going to take a little while because there's some very good stuff in here. Let me give you two quotes and then see if you can put them together.
This feels like a quiz.
The first one is from Lewis Thomas, from The Medusa and the Snail. He was at Memorial Sloan Kettering as well as a scientist, you remember. The capacity to blunder slightly is the real marvel of DNA. Without this special attribute, we would still be anaerobic bacteria, and there would be no music. So just ponder that for a second. And then here's a Ventor version. We are DNA software-driven machines. And I think one of the things that people are going to have a trouble grasping is that they sense that they might be losing Lou Thomas's nice notion of stumbling for something which is more rational and reductionistically, in a good sense, driven. Do you want to elaborate on those?
They don't have to change our view of ourselves or of humanity. The reality is the reality. We are software-driven machines. Some people make wonderful music, some make wonderful science, some write books, other endeavors that help define humanity, I don't feel diminished at all knowing that I'm software-based. That's pretty elaborate software, and it's software that allows us to adapt to our environment in a most unique way. And I talk about it a little bit of, social evolution is moving thousands of times faster than biological evolution. But now by rewriting the software, we have a chance for biological evolution to catch up with social evolution.
When I last saw you give a public talk, it was over at the Moores Cancer Center, and it was their annual industry oncology symposium. And you gave a talk that dealt with some of this work, and I wonder if you could elaborate on it a little bit, because it'll give people a bit of a clue. And it was about this, a new virus, the H7N9 virus. And I sat there stunned as you explained that a team of Chinese scientists had sequenced the virus, posted it on the internet, and then at the request of the US government, you downloaded it, and in 10, 12 hours made the virus.
That's totally accurate.
Could you now elaborate what on earth that means? And also build in the whole notion of the digital and analog ones and zeros too.
So the thesis of the book, going through everything, is that the DNA world and the digital world are becoming rapidly interchangeable. When we read the genetic code, I describe it as digitizing biology. And we've been doing this basically since Sanger's sequence of the DNA virus FIX174 in 1977, and up through the human genome and then well beyond. We've been filling the databases with digital code that describes the DNA code. And now we can go the other direction. We can start with the digital code and recreate the DNA code from 4 bottles of chemicals. And that's basically what happened with the H7N9 flu virus. It's interesting because we've been working with BARDA and the US government and Novartis trying to find a way for synthetic genomics to speed up vaccine production. And you have to go back to the previous pandemic, H1N1 pandemic that started in Mexico City. I got a call from the mayor of Mexico City asking if we could sequence that virus to help speed up a discovery, but they could never physically send that virus out of Mexico City. It got caught in all the red tape of, here's this most infectious agent and you can't send it out. For all kinds of reasons. It got very complicated. They didn't want Americans to solve the problem for Mexico. Mexico City didn't want to be known as the source of this new pandemic. The US government didn't want to receive the virus. So all these complications all of a sudden are eliminated when you can send it as digital information. And so that's what's happened with this latest outbreak in China of a potentially much more dangerous virus, the H7N9 virus, that's infecting people in China. And Chinese scientists sequenced it and posted it on the internet, and as Roger said, we downloaded it at the request of the government and synthesized it at SGI using these new techniques for converting digital information back into DNA and then biological information. And for a long time, this was the only source of this that the CDC and the US government and Novartis had of the H7N9 virus, which is now being developed into a vaccine. But it's led to a much more elaborate process, and I don't know if you want me to go into that now or not.
Let me just ask you before Craig goes on, how many of you are having trouble with this notion of digital code going over the internet and the notion of something living that's being converted back and forth like that? I mean, do you have some sense of what is going on? Can I show of hands how many people have trouble grokking this idea?
It's everybody over 30.
Right. Wait, could you just do a little slightly more on that?
On the age differences? Or
No.
Well, kids do get it because they grew up in a digital world.
Right.
So this is not stunning at all to anybody that grew up in this new world. Look, a lot of people have difficulty sort of where you started out, that even the 4-base genetic code can code for life. We can't possibly be that simple, which is why biochemists basically set back the history of science by at least 50 years by refusing to believe something as simple as DNA could be the genetic code. And it wasn't until some pretty irrefutable experiments were done in 1944 by Avery and colleagues that the beginning of the end of the proteins being the genetic material happened. But this basically, you're older than I am, I think. This all happened in your lifetime.
I don't think so.
Let's vote.
But I'm.
You know, there's been resistance from that, you know, throughout modern history of biology, starting in the 1900s. So it takes it a step further when you can reduce that 4-base code to 1s and 0s in the computer and have it be interconvertible. It doesn't seem illogical at all to me, because every life form on this planet is a DNA-based software system. And so you can do what Loeb talked about in the 1800s of recapitulating all of life if you had a basic protoplasm. In theory, you can recapitulate all of life if you get back to the genetic code. And the fact that we can transmit that at the speed of light and convert the 1s and 0s back into the 4 bases of genetic code, you know, to some people, it's really stunning, and to other people, it's like, you know, really, you thought of this? This is something new. So, you know, we get the wide range of things with it. But the implications for this is we will be able to download biology from the internet. At SGI and the Ventor Institute, we can do this now. So we can download insulin from the internet. And we can download simple viruses like 5X174 and infect E. coli and kill it. And what we did with the first synthetic cell is we downloaded the entire code, and Dan Gitsham's team made a 1.1 million letter genome, starting with 4 bottles of chemicals, that led to a self-replicating cell. So all of life as we know it can be sent as digital code through the internet or as an electromagnetic wave. And we can talk about Mars later if you want.
Yeah. The reason that I raise that question is that in every one of these pieces that which have been generated by the book and the tour, I can only assume that the editors must all be ancient because they all deal with this point. Ventor shares his vision of the household appliance of the future. It's a box attached to a computer that will receive DNA sequences over the internet to synthesize proteins, viruses, and even living cells. And this is often couched in terms of being science fiction-y. So plainly, it's a bit of a novelty to some of these people as well.
Well, you know, the notion of teleportation is something most people grew up with fiction. It didn't start with Star Trek and Beam Me Up, Scotty. In the UK, Doctor Who had his telephone box that could transport him anywhere throughout time. This has been part of fiction, even going back to Arabian Nights with being able to move on magic carpets. So humans have thought about teleportation. They didn't think of the mechanisms for doing this. And it's like quantum teleportation now. You can't send physical entities with quantum teleportation. You can't do it with bioteleportation. One of the founders of quantum teleportation said, you send a blueprint for a 747, you don't send the 747. And that's what we're doing with life. We're sending the code that codes for life, which is based on 4 chemicals. It doesn't take a whole lot to think about regenerating that from the digital code as we store it. And if you can reform the DNA, you can reform life.
Okay. Let's do a little bit of this book is essentially now past, now, and future, to be crude about it. But so let's do a little bit of the past thing, because there's a very famous book by Schrödinger, which I see you have a copy of there, called What is Life? And that book was enormously influential. Came out, it was lectures that he gave in 1943 at Trinity College, Dublin, published in 1944, had a huge influence on a number of people, actually a number of people in this area as well. Francis Crick was a physicist at the time and shifted from physics to biology, thinking that biology was far more important. Leo Szilard, who first suggested to Jonas Salk that perhaps this was a good place to build the Salk Institute, was another of those scientists who thought that Schrödinger's book was important, and shifting and concentrating on biology was hugely important. So that's a slight background about Schrödinger's book. You then, 70 years on, delivered a second set of Schrödinger lectures on the same topic, what is life? Would you just talk about that for a little bit?
Yeah, no, it was an invitation, probably if I was not in the middle of writing this book, I would have turned down, but I was asked to give the Schrödinger lecture in the same place that he gave it originally in 1943, and talk about how modern science can update what he tried to do of give a definition of life based on everything we now know. And the book is in part based on this lecture last summer at Trinity College, but in part on a much earlier history and the ongoing work at the Ventor Institute and SGI.
All right, now, so what has changed since Schrödinger, and what was so insightful about what Schrödinger said that later led to Francis Crick writing him a little note and talking about aperiodic crystals?
Yeah, so what Schrödinger had unique insight at a time even when all the leading biologists were saying proteins are the genetic material, because DNA is just a simple polymer. It's way too simple to code all of our genetic information. And Schrödinger reasoned that he took it at face value that biologists said it's protein, so it must be protein. But he said it could be just simple side groups on the protein. And in fact, he said the code doesn't have to be complicated. It could be as simple as the Morse code with dots and dashes. And in fact, before he died, there was an exchange with an author that was writing about this with Francis Crick, who said, oh no, it was obvious to everybody that it could be simple as a Morse code. But I think Schrödinger was the first to write that down and record it. But that changed the thinking, that it didn't have to be the complexity of proteins. It could be as simple as a binary code. In fact, it's more complicated because there's 4 bases. But he also described it as an aperiodic crystal, crystal meaning that it had to have stability, but aperiodic meaning that it wasn't just a repeat pattern. And I talk about the letter that Crick wrote to Schrödinger right after he and Watson discovered the structure of the double helix, saying your definition of aperiodic crystal is a very apt one. And so I think we remember Schrödinger not only because of, it helps to be right in history, to be remembered, but also because he tried to ask the question I think that nobody had thoroughly asked before: does life obey all the laws of the physical universe, or is there some unique property about life that has not been picked up by physicists? And he concluded that life obeys all the laws of physics. So Schrödinger avoided a definition, and a lot of physicists, Richard Feynman, have argued, and I quote him in the book, of trying to over-define things is dangerous, and you get to sort of meaningless levels of definition. But I describe it in the simplistic terms that life is a DNA software system. And more importantly, we've shown that if you change the software, you change the species. And this has lots of implications for evolution, and we find history for the software being changed very dramatically, not, as you refer to, with just the the simple errors in the genetic code, but evidence for very punctate evolutionary events where thousands of traits were changed in a single event. And we can go into that if you wish.
Okay, go on.
Okay, so what we found was very important was my friend and colleague on all this work is Hamilton Smith. We've been working together for years. He got the Nobel Prize in 1978 for discovering restriction enzymes. And these are the tools that probably made the molecular biology technology useful, because you can precisely cut DNA at prescribed base pairs. And it was never totally clear why restriction systems developed, at least to me, until we did these experiments of putting a chromosome from one species into a recipient cell, and that recipient cell turned into what was described by that genetic code that we put in.
Mm-hmm.
And what we had to deal with, and I described the dead ends and trial and errors that we had because, in fact, of restriction enzymes and whether the DNA was methylated in yeast and other very complex technical problems. But when there's a mismatch in the DNA in the restriction enzyme system, for example, when we removed the restriction enzymes from the recipient cell, we could just put naked DNA of any species into that cell. And so imagine the meal that you had tonight. If you had fish for dinner, and so you've consumed billions of fish genomes in your meal, that tomorrow morning you started sprouting gills, which is what happens in the bacterial world if they take up a new chromosome. They add 1,000 genes and 1,000 traits in one single evolutionary step. And then we see steps like the formation of the plant world by taking up an entire algae cell with a photosynthetic system in it, and that genome gets maintained. And our energy power plant, the mitochondria, was taking up an entire bacteria that continues to replicate inside our cells and is our energy system. So we see evidence for this throughout the biological world, and it was quite surprising to many, even people like Carl Woese. We had this very famous argument early on after we sequenced the first 2 genomes in 1995 of what to do next. And there was a big push to sequence the cholera genome. And Carl said, don't be silly, it's really a waste of time to do that, because the 16S RNA in cholera is almost the same as E. coli. Cholera is just going to look like the E. coli genome. An important piece of philosophy that I learned here as a student with the late Nate Kaplan is don't talk yourself out of doing the experiment. And so I insisted to do the experiment anyway, and it turns out cholera has 2 chromosomes, one that does look like E. coli, and one that looks like it came from a totally different part of the tree, and added all these traits to it that we now know as the cholera species. We find thousands of cases of this with sets of chromosomes that the chromosomes did not obviously co-evolve. So when you get a mismatch of restriction enzymes, if you eat something or even your neighbor contributes its DNA to you, it can change who you are as a species. Obviously, evolution would be pretty messy if there weren't restriction enzymes and every time you bump into somebody else, you absorb their DNA. If we did that, I would end up with hair.
And what would I get?
Oh, so many things.
When I quoted Lou Thomas at the beginning,
Yeah.
capacity to blunder slightly.
I thought you were referring to me.
No. Actually, Craig just got back. He's been on the road. He's been talking about this book and so on. And this weekend, he came back here and actually did that pedal the cause, that big bike race. I don't know how you get the energy to do this, but maybe that's what I get, the energy.
Yes. I'm still recovering, though.
Still recovering. The reason that I mentioned that was that what you're talking about is re-engineering the genome in a much more logical fashion.
Yeah.
In other words, you're saying that there is a better way of doing this.
Yeah. Evolution is really messy. So all these people that want intelligent design need to look to the future, not to the past. And so we're actually thank you. I think Ham Smith on the team came up with the notion, we're defragging the genome by taking this messiness away and organizing genes by function in a logical way, because if we're trying to do design, you want to have cassettes for energy metabolism, cassettes for replication, et cetera. And so we're trying to reorganize, redesign a cellular genome in a logical fashion for this future phase of evolution that we're now entering.
Okay, so let's just pop back a little bit. We'll come back to this in a second and go to Mars and all sorts of things. But could you just give me some sense of how this all began for you? Just think back, not even before UCSD and so on. How did you actually get interested in science, or what was growing up like for you?
My career that's described in my first book, A Life Decoded, gives parents hope. Gives me hope about my own son. I was a late bloomer. I hated school. I built boats. I took part in sports, chased things, and almost flunked out of high school. So I actually moved to Southern California from the Bay Area to take up a surfing career. And I found it doesn't pay to be blissfully unaware of things, because shortly after I did that, I got drafted off my surfboard and ended up as a corpsman in Vietnam. And that changed my outlook of life. I actually came back with the notion, because I was practicing medicine, jungle medicine, major surgery. It was a really fantastic learning experience for my type of learning. And I came back with the intention, actually, of going to medical school and eventually going back to be a third world physician. And it was actually UCSD that changed my direction. It was just from a couple of professors here as an undergraduate, Gordon Sato, who's still on the planet, but not at UCSD any longer. I think you knew him well, and Nate Kaplan. And as an undergraduate, they introduced me to just playing with some cells in culture. It was actually beating heart cells. And Nate Kaplan gave me my own laboratory and started me off in a new direction where I learned you could just ask basic questions about life and get answers. And it was very rewarding to do in an environment where I was never exposed to that before. And I was so hooked on it. I've published my first paper here as an undergraduate. And all of a sudden, medical school seemed like a boring thing to do. So I started down a career that, as Lippmann's mentor, Fritz Lippmann, said, the wanderings of a biochemist. My career has sort of followed where the data and the research has taken us. And I don't think we have enough time. There's a book or two out there on it, how it led to this point in time. But it's from not being afraid to ask new questions, go in new directions, and do what other people think is risky, even though it's not so risky.
Yeah, I don't want to dwell on this, but it's been written eloquently by several people about how you actually swam out to sea at one point and with the intention of not coming back, and then basically said, what am I doing?
It was a WTF moment.
Yeah. What impact did that have on? Well, it's huge. I would have thought.
I mean, as I turned 21 in Vietnam. That's going from a California education to that education was a life wake-up call. People came out of that in different directions. I was lucky; it took me in a positive direction.
So do you feel like the number of things that reference speed and in these pieces is kind of amazing? I mean, the book itself, Life at the Speed of Light, I know that's a reference to being able to transmit things, but I'm looking back at the piece in the New York Times. which was written by Will Hilton, where he's talking about, first line, that you're thinking of a bug. But he's thinking of a bug that could swim in a pond, soak up sunlight, and so on and so forth. He's thinking of a bug that could live in a factory and gobble exhaust and fart fresh air. He may not appear to be thinking about these things. He may not appear to be thinking at all. He may appear to be riding his German motorcycle through the California mountains, cutting the inside corners so close that his knee pads skim the pavement. This is how Ventor thinks. He also enjoys thinking on the deck of his 95-foot sailboat. And so on. There's references to your racing, riding your bicycle to the airport, racing passenger jets down the runway. There's an awful lot of references to speed in here, and even if I could extend that to the so-called race to do with the human genome, it's as if you look at these things and say, that's what needs to get done, and what's the quickest way to do it?
I contend that people in science and medicine study things that are very close to them. My doctoral thesis was basically on how adrenaline works. So I am probably an adrenaline addict and enjoy speed and other things, but also I think it came out of what I learned in Vietnam. Life is short. Sometimes for people, and a lot of people my age at the time, extremely short. And we have a limited time to accomplish something. So speed is essential in trying to do things. And Ham Smith and I have a rule that we don't take on new projects unless we think we can get them done in our lifetimes. He just turned 82 and still works in the lab every day. I just turned 67, so in theory I have a longer runway, but we don't know, and that's part of what the genetic code can tell us in the future, and ways to change it can change that runway a little bit, but I think speed is important. The motto at Celera when we sequence the human genome, and Celera is based on celerity or acceleration, was speed matters, discovery can't wait. And so, it would be a lot better for everybody if science went a whole lot faster. I argue the American public shouldn't be so sanguine about the slow rate of discovery with the billions that get spent, and that we should have 10 times the pace of discovery, and that my multidisciplinary small institute should be a model for maybe how to conduct science, because it's now been very successful over 20 years with many breakthroughs, having small, expert, multidisciplinary teams that are highly motivated to do things. The other thing I discovered is most people like to work on a project bigger than themselves where their expertise can contribute to making a difference. That's the opposite of what we do at universities.
Talk a little bit then about the interrelationship between, I'm thinking about science and society issues here. One of the questions I always ask people is something that President Obama said when he came into office the first time around. He said that his administration would restore science to its rightful place. Didn't give any coordinates. And I like asking people, what is the rightful place of science? And this, connected to that is this relationship between science, industry, academia, and so on. And you've thought about this a lot, so.
Yeah. So I think the main thing he accomplished was in his first week of office when he got rid of the stem cell ban. Even though it became irrelevant for science with iPS stem cells, just getting religion and politics out of science sent a strong message. Since then, I'm not sure science has reached its rightful place, and what I describe as the rightful place is science is no longer an option for society. Our future is based 100% on science. And we have a huge group of people in Congress and in government that, being described as anti-intellectual, would be giving them too much credit. They're obviously not here tonight. And we can't ignore science, we can't ignore education. We can't pretend the world's not changing. I was born in 1946, about 5 years after you. There's now 3 people on the planet for everybody that existed the year I was born. So in our lifetimes, the world population has increased 3-fold. We're struggling how to deal with that. We try to pretend that we're still in the 1950s and that's when society was at its peak, but you know, that was several billion people ago. We're going to peak out, if all the numbers are at all accurate, around 10 billion people. That's 3 billion people more than we currently have. We can't feed them. We can't provide clean water. We can't provide medicine or housing for them. And we're destroying our environment in the process. And somehow sticking our heads in the sand is the solution to politics, trying to make the U.S. A second generation loser in the world. There's more innovation in this country than anywhere else on the planet, but we have a system that's trying to kill it off right now. These are not options for our future. Countries come and go all the time throughout history. What a sad thing if this becomes one of them that goes away because of the ignorance that's enveloping it. Other than that, I have no opinion.
Yeah, I'm not going to dwell on this either, but just to reference it, the Genome War was the title of Jamie Shreve's book, How Craig Ventor Tried to Capture the Code of Life and Save the World. Throughout these early books that were written, and including your own, it's all very dramatic. There are all these characters like Francis Collins and Jim Watson storming in and storming out, and a whole group of people. There's this industry fighting against academe. There's the Brits over there with the Wellcome Institute getting irritated about various things. It doesn't sound like a very collaborative scientific enterprise at that point.
You think?
I do. I do. And yet, so in this new book, and actually even in a couple of the denouement moments in the Genome War, what I took from this, I'll be honest with you, is that you had a much bigger picture in mind. And when you realized, there were some moments I thought, and correct me if I'm wrong, where you just saw the big picture, saw what would make society flourish, and actually then drove at your own speed, the best path to get there.
I think my mind works differently than most, which is...
You think?
Perhaps why I didn't do well in school early on. I found recently with a brain scan why that might be true. I have a relatively small hippocampus. It's the only thing I have that's relatively small. My son has a photographic memory. I have an anti-photographic memory. I can't remember pictures. If I look at your face and close my eyes, it goes away. All things aren't bad, but it's...
Well, I'm so glad I volunteered to do this.
But I have to think in concepts because I don't have all this material memorized. And as concepts of putting complex information together, the future is very clear to me. There's never been a doubt on any of these things. And I reflect in the Life Decoded, after we finished the human genome, looking back all the reasons our giant experiment could have and even should have failed, but it didn't because of the extraordinary people on the team that made it work. And one of my previous colleagues who has recently died said, and Ham Smith sort of buys into this, is that I can be diving off a diving board into an empty pool, and it's the team's job to fill the pool before I hit the bottom. And that's pretty much what they do. But people in these circumstances rise to extraordinary levels. They surprise themselves and they surprise their colleagues. And we don't push people in the positive direction enough to get these super accomplishments. My accomplishment was putting a great team together and giving them the vision of where we had to go. The team accomplished this work. I didn't sequence the human genome. I was the orchestra conductor, but I drove people to do things that they didn't think they could do themselves. And one of my most famous Ham Smith quotes is, when I came back from Applied Biosystems, they showed me their breadboard device for this new capillary sequencer that I thought was going to change everything. And by the way, they offered me $300 million to set up a company to sequence the human genome using their machine. I went back and told Ham Smith what I'd saw, and that they wouldn't fund the institute, so I had to leave to form a company to do it. And his response was, "I don't think it will work, but I'm going with you."
You've had, it's an amazing team. Actually, since you mentioned hippocampus, and think about dentate gyrus and neurogenesis. I mean, think about the brain initiative that was announced April the 2nd. Another huge grand challenge.
With no money.
Some money. Where in fact the comparison is being made to the Human Genome Project. I mean, so as you see that being announced, what are your thoughts? And secondly, are you interested in brains?
Oh, absolutely. I think it's...
Everybody should have one, I know.
Yeah, no, it's... it's the one part of things that our simple linear biology can't explain. We have to understand the integrated circuitry of the brain, and we're not even close. I worry it will end up like the Human Genome Project without independent private efforts to move it along faster. And I hope there's real money that is put behind it. But I hope it stirs, efforts equivalent to ours to try and go faster. And there's lots of them out there, so I'm more optimistic that might happen.
Did you ever think of doing anything else? I mean, are you a frustrated opera singer, or?
Motorcycle race car driver, surfer.
Anything fast and dangerous?
More or less at the time, yeah. And also I didn't give a lot of thought to it. You go where adrenaline takes you.
The history thing that you mentioned there.
I thought about being a writer, and I'm still trying to do that, but I wouldn't want to make a living doing it.
Well, except this book, obviously, how long has it taken you? Because this is a very, as I said, a reflective book. This is a book that, is, as I said, is prospecting a future as well.
It took a career to write it, but in reality, I spent 4 years on it. The first 2 years were reading about 50 books. The history that I compiled in the first third or so of the book, I could not find anywhere, and I was just fascinated by it. It's important, I think, to know where we are and sort of where things came from. And even when you think you have a novel idea like making a synthetic cell, there was a book written in 1901 by a French scientist, Letec, who said, not only will this be possible one day, he was so certain it would happen, nobody should be surprised when synthetic cells come along. They were even described, in the 1600s. So people have been thinking along these lines. They just didn't have the tools to do it. They didn't know that proteins existed early on, and they didn't know that DNA was the genetic material. But the so-called materialists have been, going back to Aristotle, a key part of thinking that's been totally pushed aside in society because of religious thinking. But I argue in the book that belief systems, whether they're religious or scientific, set back science equally. And the belief that proteins were the genetic material set back science a good 50 years.
Given the climate, given what you've described, given all the things that you've been through in terms of the scientific establishment and industry and so on, what would your advice be to a young scientist at this point?
So, yeah, I would definitely restate the advice that Nate Kaplan gave me. And he is somebody that I think, like me, has lots of ideas all the time. To him, ideas were a dime a dozen. And so an idea that was meaningful was one that got put into action, got translated into something meaningful. But to accomplish that in science, you have to couple that with risk-taking, because the scientific establishment will try to steer you away from taking risk. NIH doesn't take risk with funding. If you try to take risk with what you're proposing, you won't get funded. And most breakthroughs, every breakthrough that I've been associated with, came from independent funding, not from government funding. It's clearly written in the book. We tried to get funding from Francis Collins with our proposal to sequence the first genome with the shotgun sequencing method. And they were so certain that it wouldn't work that even we presented evidence that it would a month before we published the paper, they still didn't want to fund it. We were trying to keep NIH from being embarrassed by it, and they turned it down with prejudice. But the second we published our paper, 3 government agencies stepped up to give us all the money we could ever want to do things. So you can't get money to do the risky experiment that changes it. Once you change the thinking, you can get all the funding you want to follow up on it. We need to change that.
I assume you never thought of going into politics, though, right?
No. I would last really long in a political campaign.
Talk about science fiction. A number of these pieces have made the obvious point that you're converting science fiction into science fact and so on. Did you read much science fiction?
I read a little bit. We talked about Ray Bradbury earlier, and only out of all the interviews I've done, there was only one person who picked up that I refer to the 3 laws of robotics in the book, and even the very few people know there was a zeroth law. Yeah, Asimov.
Yeah.
And I was surprised going back to look that Asimov was actually a biologist. He didn't start out as a science fiction writer. He started out as a research scientist and went into science fiction. And the good science fiction is something there's a very close tie to reality with. Science fiction that's just vanity stuff, vanity ideas, really doesn't carry anywhere. So I think science fiction is important, especially if it points the direction to where we might go.
When I asked Ray that question, I asked him a question at dinner with Arthur Clarke was there as well, and I said, what you're doing is trying to predict possible futures. And Ray said, no, I'm trying to prevent possible futures. Mm. And I think that was the Fahrenheit 451 sort of notion. In the same sense, then, as people look at this and worry about the possible dark side of all of this, what do you say to them in terms of worrying about this being mishandled?
Yeah. So it's one of these challenges that I think all scientists have, and I view that every scientist has a public responsibility to speak out about their science and where they're going, particularly if you're pushing limits like we are. And so we asked for a bioethical review before we ever did the first experiment, and we drove this long before anybody else even thought about asking these questions. And I described those at somewhat length in the book because I was very surprised by them. And we contracted with Art Kaplan's group at University of Pennsylvania, and they spent a year and a half. I was only invited to one session, bringing in religious leaders and people from the general public, and this whole notion of was it okay to make new life forms in the laboratory. And the biggest surprise to me, there's not a single religion that they brought in that had any objections to it. Basically, they sort of, like lawyers, look back at the scriptures to see if there was anything that forbade it. And in fact, this whole notion that keeps coming up in the press of playing God is a key part of most religions, and they want humans to play God to change the outcome of the human endeavor. So we've had very few attacks from the religious side of things. It's almost more from the denialists out there that don't want to think of anything changing. And I described how it's hard to have a dialogue with a recent survey that came up at the start of our book tour, that 50% of people don't know that tomatoes have DNA. And if that's where you're trying to start a national conversation, a dinner conversation, it's very difficult to talk about then changing that genetic code. And the number of people, and there's probably some in this audience that could probably get very angry at Monsanto and spew all kinds of things without understanding the least bit of what Monsanto's doing. This is a key part of the future. The fact that golden rice has been blocked from Africa because it's a GMO, when basically it could prevent 250,000 cases of blindness in kids because they don't have enough vitamin A. These should be considered crimes against humanity, yet they're considered righteous people because they don't like GMOs. Science is going in difficult directions that integrates totally with every aspect of society now. It's not, as I said, just a nice conversation to have. It's a difficult conversation.
Yeah, we haven't got much more time. I've got a couple of quick questions to end, but the things that we haven't touched on are things like your voyages, the microbes, all the stuff going on beneath the oceans and so on, which I strongly recommend you read in the book. I mean, he's been doing, the whole team has been doing an amazing job. I have two quick questions despite the bye-bye. One is, if I gave you a time travel token and asked you to bring to your dinner table anybody from any period in history, any discipline, is there somebody you'd love to sit down and talk to?
So to be fair, he gave me an advance warning of this question, so I had a chance to think about it. And I think bringing back some of these Francis Bacon,
Royal Society,
the Tank, who wrote in the 1900s about synthetic life, Schrodinger, Darwin, Francis Crick, and then somebody 70 years from now.
And then sit them all at a table.
I think it would be a fun dinner conversation.
All right, it would.
And maybe you, to referee.
I'll be too old by then. Final question, what are you optimistic about?
I hope my books come across as optimistic. You can't do front edge science without being an optimist. Or you'll do what Nate said, you'll talk yourself out of doing every experiment. And so it turns out there's a genetic basis for optimism, pessimism, but I'm optimistic about everything, even probably when I shouldn't be. I think we have a chance to take corrective action to turn this country back in the right direction. But I'm optimistic we have the ability to do that. We have a bad capacity as a species that we respond really well to emergency situations. But we have tremendous difficulty preventing those things in the first place. Understanding our genetic code is going to give us the ability to understand those futures, and I'm hopefully optimistic that we'll have the wisdom to use that information and do the same thing about our general environment that we live in.
All right. We'll take some questions now, but Craig Ventor, thank you very much. That was wonderful. So, do we have any questioners?
Chris Pickford, San Diego. We've got Asimov from Honda. We have Watson from IBM. Ray Kurzweil seems to think that solid-state intelligence is going to outdo a human. Do you think the Asimov with Watson in it is going to be nice to us humans?
So I think the notion of artificial intelligence is maybe a best description of Congress. It doesn't work with any computer system that I've seen, and look, I talk about what happened in the computer world early on in my book, and the thing that a lot of computer scientists and physicists jumped to was trying to define biology and create biological systems in the computer. And they've all failed because computer code can't evolve like the biological code can. Going back to your very first statement. Because when you get an error in the computer code, it crashes the program. Life would not exist if we were that absolute. So.
Hi, I'm a high school biology teacher, and you spoke a little bit about your experience with education given your unique learning style. And I was wondering if you could comment a little bit more about what you think the necessary skills we should be seeing in high school graduates who maybe want to pursue science, and what you think that high school science teachers can actually do about that. So kind of, what do you want to see out of high school graduates who could possibly help enhance and succeed in this new digital biological age?
No, it's an important but complex question, and you know, kids are learning in the third grade what I learned long after I got my PhD. So the world is changing very rapidly, and we have a lot of student groups that come to the Institute, including high school science teachers, for education and what's going on in the DNA world. And we had this one group of third graders several years ago that came in, and they had a choice of isolating DNA from lettuce or hamburger. And this one young boy chose hamburger. And at the end of the day, he wanted to take the DNA home. And we said, why? What are you going to do with it? He said, I'm going to go home and clone a cow. So that's pretty good for the third grade. So, you know, your challenge is tremendous. And in fact, we have a laboratory bus at the Ventor Institute that's been going around to middle schools, because all the data shows that if you don't capture particularly women and minorities before they get into high school, there's no way you're going to change their direction once they're in high school. So, but I think these new areas capture one's imagination. All I remember from high school biology is that because I was goofing off, I was forced to eat a piece of formaldehyde pickled brain. And I think that's the only thing I got out of high school biology. And you know, it's a different world now. And your job is to keep up with this leading edge and use it to excite kids. The good news is it's really amazing to me, because kids today grow up in this digital world, they don't have any trouble with this notion of biology and digital worlds being inconvertible. And so the challenge is directing them into an area like bioengineering or someplace where they can have that kind of impact.
On that note, please thank again Craig Ventor.